Good morning, Flynn. Um, Flynn, just I send you an announcement. Tomorrow is not a demonstration. Tomorrow you will go to TD 320. That's your first practical. Make sure you don't miss it. That's 10% of the total mark. Did you get that? All right. Thank you. I look forward to see you there. Don't miss it. Morning, Nguyen. Morning, Darcy.
Good morning.
Yes, morning, Darcy. Let me repeat. Tomorrow, there is no demonstration. We go to TD 320. That's next to the physics lab. That we conduct the first practical. It is 10% of the total mark. Make sure you don't miss it. I also send you an announcement, just making sure no one um, is left behind. Okay, we wait for 5 minutes before we start the class. Thank you. Okay. Good morning, everyone. Daniel. Daniel, have you seen my announcement? Or make sure you will be there. That's 10%. Now Porty is here. Porty, have you seen my announcement? All right. Good morning, everyone. Let's get started. This is the last lecture demonstration before the mid-semester test. So there are two more classes this week. Both of them would be consumed for the practical. So two practical this week is very important. Each of the practical has 10% time. In total, we have three practicals, 30%. That is to help you with an easy pass of this subject. Hope you take the chance and you don't miss it. The first one being tomorrow, the second one being Wednesday, and the third one is week 11. Is that clear to everyone? Okay, well done. Let's start this class. So we have almost finished with the truss structure. So here we want to go into a new type of pin joint structures. So with the truss, the characteristic of a truss is made of pins and two force members. So what happens if I include a number of three forces and two forces together? That would be called a frame. That would be called a machine. Okay. So here, this is a good example of, I mean, how similar this is to the truss structure. The similarity, I mean, in 1 million years, if someone thinks of this being similar to the truss, but believe me, that has large similarities with the truss structure, in that this structure is made of a combination of two force and three force members. All right. Anyone still remembers the classification we made between two force and three force? Do you still remember? A three force member has forces exerted at three different points, and the forces are colliding at one single point to be at equilibrium. But two force members can only become longer or become shorter. So for today, we were trying to solve this frame structure. So let me repeat the definition of the frame. The frame is a pin joint structure, and it has a combination of both two and three force members all together. So let's see how this would impact the solution. All right, I'm bringing this image here. All right, that's a tool. This is being used to compress a spring. Maybe you compress this spring for placing that inside the machine. So that's a special tool for preloading a spring and placing that inside the machine or assembly or whatever. Here, you've been asked to find out the forces in each individual member. All right. So when I say member, let's see how many members are here. This is one member, the lower one, which is relatively complex. How many forces are applied to this force? Anyone can tell me? So one force here, second force here, third force here, fourth, five. So this member is a 5-force member. So this is a 5-force member. So definitely the deformation of this member is not simply elongation or compression. It can bend, it can I said it's a very complex structure, the lower one. What about this one? GBA. Is it a two-force member or three-force member? Daniel, GBA. Is this a two-force or three-force member? Darcy, is this a GBA? Is this a two or three-force member? Well, that's a three-force member, Darcy, because you have applied one force here, and then the second force would be exerted at B, the third force would be exerted at A. So that member is a three-force member. This is a three-force. And this one is a five-force member. 1, 2, 3, 4, 5. And what about AE? Flynn, AE, is this a two-force or three-force? How do you classify AE, Darcy? Or, sorry, Flynn? Nguyen, what do you say about EF or ED? Are these two-force member or three-force member? Yes, well done, Nguyen. Both EF and ED, they are two-force member. And Porty, the spring. Do you see a spring as a two-force member or three-force member? Yes, that's two-force member. Well done. So today we want to solve this machine or frame, and this frame is all members are joined by pin, but this is a combination of two-force, three-force, and even more force members. And here the choice of a strategy is critical. So let's start with choosing how do I start with this structure. I mean, I have to disassemble individual members and then starting from one member, finding the reactions and transferring the reactions to the next member. Okay, so let me start with let's start with a spring. I mean, if I want to solve the spring, that is not solvable. Why? So this spring, if I release that, how many forces are there? Well, the forces are either in compression or tension. I assume that this is in compression. But then the problem is I can't solve it. So this free body diagram only has two unknown, but we can't solve it because there is no known value. It's just Fs equal to Fs, but we know the magnitude of that. So let's just start with another member. I go for this member here. Or let me release that member and see how the free body diagram for that looks like. So here, the free body diagram, I'm going to have 135 Newton applied here. And then at this point, this is point C, that's a pin joint. There will be C of y and C of x. And also, this is point G. Sorry, that is point B. So point B has also a pin, and there are B of x and B of y. And also there is a point of F. So point F, there are two forces because this is pin, that is Fx, Fy, and also at the end there will be F of S. So here I have 1, 2, 3, 4, 5, 6, 7 unknowns. So this is 7 unknown, and this is not solvable, right? So where should I start? Can you suggest a solvable part? Let me try GBA. Let's try to solve GBA. Okay, what about that? GBA. So we want to release GBA and find the forces here. So at point A, there are two reactions because it's a pin. At point B, there are two reactions because that's a pin joint. And here I have a 35 Newton applied here. So a spring is not solvable. The lower part is not solvable. The GB is not solvable. And what about CD? Let's try to solve CD. See if CD is solvable. So point D is a pin. So with the pin, you have to include D of Y and D of X. Also, point C is a pin. So you have to include C of X, C of Y. And also at the end, there is a force, a spring force, Fs, applying here. So it is solvable. 1, 2, 3, 4, 5, and only have 3 equations. So that is not solvable. Okay, so how about I try EA? Okay, EA, that's a two-force member, right? With the two-force member, we know that the forces are going to be longitudinal or axial. So let me bring that one here. So that is, let me assume this is under tension. Because this is a two-force member, I make this A, or I call this, do you remember how we use the notation of the bars inside the truss structure? That should be called FAE. And this one should be called FEA. But even that one is not solvable because this doesn't have any input. We only know that the two forces are equal. So we are running out of the options. The next option I have is ED. Let's try ED. And also I bring EF. So these are two force members. I call this FDE. And this one I call FED. So that is with the lower one, that is EF. Okay, so I made all the free body diagrams, but none of them is solvable. Who can help me with just finding a way out of this problem? Okay, let's start with this one. How many unknowns? 1, 2, 3, 4. Yeah, is this really 4 forces here? Is there a way I can make this one solvable? Just by comparing this free body diagram and that free body diagram here, can you make a conclusion? So I'm giving you a hint, everyone in the class. Can you compare this free body diagram and that free body diagram? And that is the key to solving this problem. What conclusion you can make by comparing that AE with that GBA? What comparison or what conclusion you make out of that comparison? The conclusion is when you are finding a force in one free body diagram, the very same force can be transferred to the member which is pin joined to that. You remember? All right, if you compare that free body diagram with this one, the very same force at pin A. When? Because this is a two-force member, that is the key to solving this problem. Because I know from this free body diagram that pin A only has one horizontal force. So the very same pin in this free body diagram, we generally speaking, that is a pin, and every pin should have two components. But because this pin is exerting force to AE, therefore here you should only include one force. And then now I modify my free body diagram accordingly. So this is the action reaction. The same force should be exerted here and only the change of direction. So if here I assume the force is left to right, okay, so now this force is from left to right. I include the very same force here in the opposite direction. So I make this one from right to left. Okay, now this free body diagram, is this solvable or not? Let me ask everyone, could you give me a feedback? Everyone followed how did we concluded from comparing these two free body diagrams? If you followed, just change your status. Otherwise, I would explain that again. I'm waiting for your feedback. Just change your status to, okay, Daniel. Thank you for Daniel. What about Barnaby, Darcy, Flynn, Nguyen, Porty? Barnaby, do you want me to explain again? Oh, okay. So you are good. And what about Darcy, Flynn, Nguyen, Porty? Is that clear? We made the comparison between that free body diagram here with the AE, the free body diagram for AE and the free body diagram for GBA. Nguyen, you want me to explain? Okay, good, I explain. Look, by default, Nguyen, every pin in the free body diagram, you include two forces. That's the kind of support. So because a pin can resist motions horizontal, vertical, that's a general case. But because pin A is connected to a two-force member, which is AE, all right? So AE can only apply force horizontally. It cannot apply force at an angle. Is that understandable? Because AE is a two-force member, it can only take axial force. So therefore, it should be consistent between pin A at here, that is, so here, that is pin A, and this is pin E, right? Nguyen, can you see that? This is pin A, this is pin E. And here, that is pin A, right? So because pin A in the below free body diagram can only take horizontal load, I conclude that the very same pin here, it takes the horizontal force. Do you want me to explain in different words, Nguyen, or is that understandable now? Okay, thank you. So by this little trick, by comparing these two, we find the starting point. So that is the starting point. If I solve this free body diagram, then what I find from here, I can transfer this to the rest of the free body diagram, and that would reduce the number of unknowns, and then they become solvable. This is like a domino. So once you push the first domino, the other would fall. So that is to defeat the domino. once you can solve this one, everything else would be solvable accordingly. Let's get started with this one. So what is the best strategy to solve that? I think the best strategy is to take rotation with respect to point B. So with that free body diagram, I take rotation with respect to B equal to 0. And that gives me FAE times, what is the arm of rotation for that? This is 25 millimeters. So that is FAE times 25, that's arm of rotation. And this is making rotation in a negative direction. And also 35 make a negative rotation, minus 35 multiplied. Arm of rotation with respect to B is 100. And from here, I find FAE to be equal to 140, I think. Let's just calculate. 140 negative. And the next, all right, the next is net forces horizontally equal to 0. That would tell me Bx is equal to minus 140. And then I apply net forces vertically equal to 0, and that tells me By is equal to 35 Newton. All right, now we can bring these forces back to other free body diagrams. And now that I have this force, I can reverse the direction of this one because this is negative, right? So that it means I made a mistake here. This is not tensile, that's going to be in compression. So let's change that to the compression. And that is equal to 140 Newton, right? So how this can help me? I mean, that's I need to apply method of joint at point E. So that is another free body diagram I can construct. So let me apply method of joint at point E. Why do I do that? Because point E is connecting two force member. ED is two force member, EF is two force member, and EA is three force member. So if I make that free body diagram, it would look like this one. So this is point E, and I'm applying method of joint at E. So here, that member is compressive. If this is compressive, I will have 140 applied here. And then you have to have two forces. This is FDE, and this one is FEF. All right, so now, because of the symmetry, these two forces are equal. So these two forces are equal. And then I know that 2 times FDE. So I know that FDE is equal to FEF. This is because of the symmetry. And 2 FDE time cos of this angle. So I need cos of this angle, which is, that angle is 60 degrees. Cos 60. That is equal to 140. So 60 cos is equal to half. Therefore, I conclude that FDE is equal to FEF is equal to 140 Newton. All right, so far so good. We managed to have this free-body diagram solved. This free-body diagram is solved, and that free-body diagram is solved. So what can we do now for this one? For example, CD, because at point D, I can substitute the force. So D is connected to a two-force member. Once I have FD, let me clear these two forces and substitute those by the force, or I'm transferring the force from another solution here. So that is point D, and I know that D is under tension or compression. D is under tension. So if D is under tension, I have 140 applied here at an angle of 30 degrees. So how many unknowns are here? 1, 2, 3. So that is solvable. I take rotation with respect to, this is point D. I take rotation with respect to point D equal to 0, and that gives me Cx is passing here, 140 is passing here. So that is F5 multiplied by Fs multiplied by arm of rotation. Arm of rotation for that is 75. That is equal to Cy multiplied by the arm of rotation, which is 75. So here I find force of a spring is equal to 140. And then I can work out the horizontal forces. So to find horizontal forces, that is 140 times sine 30 is equal to Cx. I think I made a mistake here. So this one has two unknowns. We cannot solve this. So to solve that I have to take rotation with respect to point C equal to 0. I take rotation with respect to point C equal to 0. So that is Fs multiplied by 2 times 75. That is 150. Fs multiplied by 150, that is equal to the vertical component of 140. Which is 140 cos 30 multiplied by 75. So 75 cancel from both sides. This is 2. That is 70. So Fs is 70 time cos 30. 70 times cos 30 is 60.62. All right, so here we found Fs. Now you can work out Cy and Cx. So Cx, Cy can be found from here. And then I bring these two forces to the last free body diagram, which is here, because I already know the forces at C. I know the forces at F. And here, Fs also is known, so we can solve this free body diagram. All right, so this problem was an example of the frames, and you don't expect something like that for the exam. Exam would be far simpler. That was just to demonstrate how a combination of pin joint members can come together and make a structure. So we have the full solution of this problem into the slide. You can find out individual forces here. So let's move on to the next problem here, that is pulleys. So another type of machines that is utilizing pulleys. Pulleys are helping us in two ways. First, they are changing the direction of the force. Sometime in a compound pulley system like this one, you can magnify the amount of the force. So here we want to use that. You want to solve that system. Let's do that again. Okay, here this system has two pulleys, and there are two weight systems here. The first one is 75 that is exerted here. Also the seat has a weight of 75 Newton. So there are two weights have to be exerted here. Let's try making a free body diagram from here. All right, so we make a free body diagram from here. So with this free body diagram, I need to include 750 plus 75. So that is the weight of the seat plus the weight of the person. And then because I'm cutting through this cable and that cable here, there are cables can only take axial forces. So there is one force here and one force here. Let me call this one TA, tension at point A, and I'll call this one tension at point E. Can we solve this problem? We can't, because in this problem, this is like a one-dimensional problem. In one-dimensional problem, you only can have one useful equation. So net forces doesn't tell you anything. Net forces vertically is the only useful equation you have. The net forces horizontally is not useful, and the net rotation is not useful in here. So that free body diagram is not solvable. Is that clear? So I do need to go for another free body diagram. Let me isolate this free body diagram, this pulley. I'm isolating pulley C, and what do I get is so here I have one tension at this rope, and this tension is equal to tension at A, TA. And then there will be two tensions on both sides of the pulleys, right? But just take this as a recipe. If the pulley is frictionless, the tension on both sides of the pulley are equal. I can prove this for you. Just let's take the rotation with respect to the C. If I take they are not equal, this one I call this T1, this call like this to T2. I'm going to prove for you that for any pulley, T1 is equal to T2. How this can be done? Just take net rotation with respect to C equal to 0. And here, because this is radius, and this is the same radius, right? T1 times R is equal to T2 times R. So you cancel R from both sides, and you get T1 equal to T2. So that was the proof. In the exam, you don't have to prove this. So just remember that with the pulley system, the tension on both sides are equal. So I call this T, that one I call same T to indicate that they are equal. So I call them simply T. All right, what can we say from this free body diagram? If I apply net forces vertically equal to 0, that tells me 2T is equal to TA. All right, so that's a useful equation. Let's keep that, and then we use this later on, all right? The next thing that I do is I would like to isolate this one. So let me isolate or make a free body diagram of the pulley D. So if I make a free body diagram from the second pulley, so what are the forces? There is one force at point D, which is holding this to the roof. I call this dy. And then there are going to be two forces here, right? All right, so here I can say that both sides of this pulley are equal because this side is consistent with this one, that is T, and this one is also T, right? But now let me make my free body diagram a little bit larger. So now I'm making my free body diagram here. So last time we cut this below the first pulley. Now we are cutting that above the first pulley. So let's see what happens this time. So if I cut this above the first pulley, that's what I get. So the weight is 750 plus 75 Newton. And this cable, I found this to be T. That one, I found that to be T. And this one, I found that to be T, right? So simply, I can solve the net forces vertically here. And that tells me 3 times T is equal to 825, which is sum of those, 825 Newton. And therefore, tension in each pulley is 825 divided by 3. That is 275. I miss TA. No. Nguyen, that is the free body diagram above the pulley, not below the pulley. So below the pulley, that is TA. That is when I cut this from here. It only has 2 tension. This is this free body diagram. That's free body diagram number 1. This is free body diagram number 2. That is free body diagram number 3. And this is free body diagram number 4. So the 4, I'm not cutting that from here. I'm cutting that from here. You see the difference? So if you cut this below the first pulley, you only get 2 tension. That is what we have in the first free body diagram. But if I cut this above the first pulley, I will have 3 tension here, which are according to free body diagram number 2 and Nguyen. Do you see the difference between the free body diagram number 1 and 4? All right, thank you for that. Now that I've calculated T, we can go back and calculate TA. So TA is 2 times this one. So therefore, TA is 2 times 275, which is what? 550. Okay, if you have to make a conclusion from this problem, does this make sense? What this man did, does this make sense? Yes, it does, because the compound pulley is helping him. If he wanted to overcome the total weight, he has to overcome 825 kilonewton. That is something like 82 kilogram. That is too heavy. You cannot even lift it. Okay. But now this guy is only applying 550. And the second advantage here is instead of it is easier for you to pull something to push it, to lift it. So he just not only reduced the magnitude of the force, also he changed the direction of force to be applied. So it's easier for him to pull this down rather than just lifting himself up. Okay, questions. Did you follow the solution? If not, just let me know. I'm happy to explain again. So we got, I think, Chase, Sal, and Barnaby, they came after my announcement. Have you seen the announcement yet? Chase, Sal, Barnaby, do you know that tomorrow, instead of the demonstration, you have to go to the TD 320 for the first practical? Did you hear that? Thank you, Barnaby. And what about Chase, Sal? Chase, Sal, are you with us? All right, Chaisal, maybe you're not in the class. If you're watching this later, make sure you don't miss this opportunity. That is 10%. You don't want to miss it. Thank you. All right, going back to the slide. All right, the next topic is about the internal load. So we are already familiar with the internal load inside a truss structure because truss structure is made of two force members. The internal forces are easy. So if I have a two force member and that two force member is subjected to two force, so this is my two force member. And then if I apply, for example, 5 Newton on each side, making this under tension. All right, so here I have a choice of cutting this from point A or cutting this through point B, or if I cut that through point C. So if I cut it through point A, that is what I get. This is 5. This is TA. If I cut it through point B, I have 5 and TD. If I cut this through point C, so I give you 5 minutes, and 5 minutes is find internal forces TA, TB, and TC. I give you 5 minutes. Can you find these forces? 5 minutes from now. Okay, 5 minutes up. So who has the answers? Chaisal, can you tell us what are the internal forces? TA, TB, TC. Daniel, Flynn, Nguyen, Porty, or Barnaby? Just by looking into the above free body diagram, that is a 1-2 force member, 2 equal forces are applied at both ends, 5 Newton, and then we made 3 sections at point A, B, C. So each of which are making one internal force, TA, TB, TC. Can you tell me what these internal forces are? That's a very simple question. I'll be disappointed if you cannot answer the question. Nguyen, Porty. Okay, so this is a very simple question, very surprised that no one answered the question. So here you just write net forces horizontally equal to 0. So TA is equal to 5. And here you apply the same conditions. And then you get TB is equal to 5. And then here you apply the same condition. And then you get TC equal to 5. 5, 5, 5. Do you follow that now? Can you just give me a feedback? I don't feel I'm talking to class. Just let me, if someone is listening. All right, thank you. So here my conclusion is, when you are dealing with the conclusion is very important. I want you to remember that conclusion. When you are solving a truss structure, the internal force doesn't change in the x direction. So this is the x direction. That's a longitudinal. It's an axial or longitudinal direction. With the truss structure, the internal force does not change axially. So this is in contrast with some more advanced component which we learn later on, something like a beam. A beam is a member which changes its curvature due to the bending. So with that, once you go from one point to another point, once you increase x or reduce the x, the internal force would change. But these are such a nice creatures, the two force member, the internal force doesn't change. And that is a very important conclusion. All right, now we want to just start a new background, and that is we want to start studying the bridges, the beam structure. So beam structure is the complex, and in that the forces are distributed. So that is an example of a distributed force. So imagine you have a bookshelf, and in one scenario you just put one big textbook in the middle, and that applies the force as a point load. But if you have a number of textbooks distributed over this horizontal shelf, what you get is a system of distributed force. So here is what I said. I noticed that almost from here to here, the height of the books are almost, the average height of the books is that much. And suddenly toward the right, the books are, the average is a little bit taller. Okay, so the taller they are, the heavier they are. So for that, I take a lower value. For this one, I take a higher value. But then my question is, why the unit for these forces instead of Newton? Why the unit is Newton per meter? What does Newton per meter means? So Newton per meter, that means 1 meter of this load is worth of 30 Newton. So for the right-hand side, it means 1 meter of that load is worth of 50 Newton. So what if I have half a meter? So if I have half a meter, that would be 225. With the left one, if I have half a meter, that would be worth of 15 Newton. Okay, so that is a very common situation in the building. In the building, some of the load are not point load, they are distributed load. So instead of having the load itself, you know the intensity of the load. So that is the intensity of the load. So intensity could be per length, or intensity could be per area. So here we've been provided with the intensity of the load, and the intensity could be per length or could be per area. So here this is per length. All right, the next question is, if I have to solve the forces here, how do I handle this situation? I mean, this is not a Newton case. So I need to simplify that by replacing the distributed force with a point load. And that is not complex, especially in this case that we have a uniform distribution. Does that make sense? This is a rule of thumb. If the distributed load is uniform, I want to replace that with the resultant force. Where should I put that resultant force? Should I put it at the left, at the right, or right at the middle? So let me send this question as a poll to everyone. I want to hear your answers. Okay, now I'm posting the quiz. And would you please answer this question? Okay, can I get you responding the poll, please? All right, now I got one correct answer from Nguyen. Well done, Nguyen. And what about everyone else? Forty, Flynn, Daniel, Chaisal, Barnaby. Would you also? Okay, Daniel thinks none of them is correct. And what about Porty, Flynn, Chaisal, Barnaby? Barnaby is correct. Barnaby, Nguyen, your answer is correct. Daniel, you want to reconsider? Just read the question again, Daniel. Chaisal, Flynn, Porty. What about you? Chaisal, reconsider, read the question again. Porty is correct. And I'm waiting just for the Flynn. So I don't have answer from Flynn, but all answers are correct except Chaisal and Daniel. Or would you want to change your answer? You can change your answer if you think another answer is correct. All right, the correct answer is because the load is uniform, the resultant should be located right in the middle. Okay, so that is two things you have to remember. Before we solve a system with the distributed load, we need to find its resultant, and also we have to find its line of action. Line of action means that if I'm replacing that distributed force with one single load, that is called a resultant. And then where this resultant should be located from the left x, that is called line of action. Line of action. That means where should I put that resultant? So in this case, that is very simple. This is simple because the distribution is uniform. Let me give you a more challenging case. So in this challenging case, imagine that I have a shelf, and on this shelf, my shelf has two supports, one support here, one support here. And then I managed to find a number of books which are gradually, they become larger, larger, larger. Okay, so with this distributed force, we notice that this is resembling a pattern of a triangle, right? So if the tallest part of this triangle is, for example, 30, and the span is 1.5 meter, that is 30 per meter. So I want to find a replacement for this distributed load. In another word, I want to find a resultant force. That resultant force is equivalent. I can replace that distributed load with one. And also I want to know that how much this resultant is away from the left edge. So if this is my coordinate system, y, x, I want to know this resultant, the magnitude of the resultant. Also, I want to find out that x bar. X bar is distance of line of action. How far this resultant should be from the left edge. So anyone can give me, I mean, even without I telling you the theory, can you make an educated guess? So in the case of the rectangle, what did we do? In the case of the rectangle, I just found the area of this rectangle. The area was, the vertical was 30, and that was 1 meter. 30 multiplied by 1, that is the area under the curve. So that is 30 Newton. So in another word, 30 Newton per meter multiplied by 1 meter. So you cancel this meter, and the answer is 30 Newton. That is the resultant. So can we do the same thing here? Here, I want to find the resultant, and the resultant, I find the area under this, the area of this triangle, and the area is what? That is 30 Newton per meter. This is Newton per meter. Newton per meter multiplied by 1.5 meter, and then meter cancel, and that is 45 Newton. So that is the resultant. Is that clear? So in another word, when you are given a distributed load, to find the magnitude of its replacement point load or resultant, you have to find out the area under the distributed load. So this is like an integration. You integrate under the blue line, and that integration in this case is the area of the triangle. It could be a quadratic curve, it could be a uniform distribution which makes a rectangle. Okay, And now the next question is, do you reckon R, is this right in the middle? Is this closer to the left, or is this closer to the right? So who can answer this question? Barnaby, do you reckon that R, the resultant load of a triangle, is this closer toward the left or closer to the right, or just closer to the right? Well done, Barnaby. And then that makes sense, isn't it? Because this right hand side is heavier than the left hand side. So according to the Barnaby, I have to bring this one to here. All right, everyone listen to what Barnaby said. He correctly says that for a triangle, the resultant is not located in the middle. That would be more toward the right hand side. And how close? That is the centroid of the triangle, center of gravity. And you remember from geometry that the centroid of the triangle is 1/3 of the, so if this is 1.5, that is 0.5, and this side is 1 meter. All right, so line of action for this one is equal to 1.5, and the magnitude of R is 45 Newton. So, I mean, there is a calculus mathematics behind it, but you don't like the mathematics, just take the recipe. Whenever you are provided with a distributed load, all you do is you find the area under that curve. So in this case, my intensity is has the same dimension as the pressure. The pressure is Newton per square meter. This is not a linear intensity. This is a planar distribution. It is expanded in y and x direction at the same time. So that pressure, the unit for that pressure is Newton per square meter. This is something like you remember from fluid dynamics in energy and motion that the pressure unit was Pascal. That was Newton per square meter. This is like intensity in 2 dimensions. So how do I find that? First, I have to find out the resultant force. So the resultant force is, that is the integral of Px by area. So I have to integrate over the area, and that pressure integrated over here, that is the volume of how much volume can be accommodated under the surface, right? So that is the resultant. What about the magnitude? The magnitude, I have to find the centroid of that volume, and because of the symmetry, the centroid would be along this axis. So that is the centroid of this curve. The centroid of the curve, like the previous curve, because the right-hand side is heavier, I expect my centroid to be closer to this one and farther from that one. All right, let's move on. That is the mathematical proof that whenever you want to find the resultant, your resultant, you have to take integral of the curve. So the area under the curve, that gives you the resultant. And whenever you want to find the line of action, the line of action, or x bar, that is x bar, line of action. That is the centroid of this shape. So whatever this shape is, the centroid of that is where your x bar is. So I want everyone to remember these 2 rules as the recipes. So these are recipes we would remember, and based on these recipes, we can solve problems. Next question is, all right, is there a mathematical relationship for this one? The mathematical relationship is x bar is x bar is the integral, the area integral of the x divided by area integral of the surface. Okay, so that formula we remember, and from now on we use that formula for finding the line of action. Line of action is where you should replace the resultant force to simplify the distributed force. Because we cannot solve the distributed force system, we simply find out the total resultant force, and then the next question is, where should I position it? Should I position it in the middle, or should I position it farther or closer? How much? That is by x bar. So let's go to some examples. So the first example, I have a quiz for you. Just let me run this quiz. So I give you 5 minutes. In 5 minutes, can you tell me which answer is correct? Okay, can you respond to this quiz, please? All right. Nguyen correct, Daniel correct. What about Barnaby? What about Flynn? What about Porthy? So the correct answer is area. All right. So let's go to the next quiz. The correct answer here is area. The second question is the line of action. So let me run another quiz. So can you respond to the second question, please? What is the line of action? All right, so I got one correct answer from Nguyen and one correct answer from Barnaby. Daniel, you want to think twice? You want to read the question again? What about Flynn? What about Porthy? Okay, Daniel, now is correct. Thank you. Yep, well done. Let's go to the next slide. So here I have a pack of timbers. These timbers are not loaded just flush to the wall. They are being offset by a distance of A from the wall. So here I want to find the resultant. The resultant, let's find this together. So the resultant is the area under this one. The area under that curve, R, is equal to the area of the rectangle, which is W0 Newton per meter multiplied by. And what about the line of action? So this is my y-axis. This is my x-axis. So the centroid of this one, that is A plus B by half. So x bar is equal to the offset A plus B by half. And next slide, is that clear? Anyone want me to explain? Can you follow that? Let's solve this problem. Here I have 3 packs of distributed load, and first I want to replace each of them with one single resultant. So let me call this R1. I call this one R2. And I call this one R3. All right. So R1 is equal to 1.5 times 3. This is the area under this curve. So the area under this curve, that is equal to 4.5. And the area under this curve, that is 1 times 3, which is 3 kilonewton. And area under this one is 2.5 times 1.5. That is 3.75. And now I have the centroid of the first one. I call this x bar 1. That is equal to 1.5. And the centroid of the second one, that is x bar 2, this is equal to 3 plus 1.5, that is 4.5. And the centroid of the third one, let's call this x bar 3. That is equal to 3 plus that, which is 3.75 meter. All right. Now, imagine I want to simplify this further. By simplifying further, I mean let's just replace 3 forces and replace that with one single big resultant. That big resultant is the sum of these 3. So that is equal to R1 plus R2 plus R3. That is not difficult to understand. Is 3 6 point, yeah, that's 6.75. Thank you for that. 6.75. Thank you for that. All right. Now, if I want to replace that 3 system of point load with one single point load, the resultant is just by adding these 3 forces. But what is the line of action for the big resultant? I call this big X bar. So the big X bar from the formula I have, that is X bar 1 multiplied by R1 plus X bar 2 multiplied by R2 plus X bar 3 multiplied by R3 divided by R1 plus R2 plus R3. Okay, so this is an application of the, I mean, here I replace the integral with the summation. You know, the integral can be changed by, when you have a discrete system, you can replace the integral by discrete terms. So 3 lump terms. So that is what it is. Okay, last we have one multi-choice question. Find out the location of FR. Can you tell me what is the location of FR? So location of FR, that is, this is 1/3 from the base or 2/3 from the apex. 2/3 from the apex, that is 2 meter. 2 meter plus 3 meter, that is 5 meters. So the correct answer is this one. That is FR D. What do you struggle? That is the offset, and this is a triangle. What is the centroid of a triangle? You have a triangle Nguyen. This triangle is 3 meter in base. So the centroid of this one is 2 meter from the apex and 1 meter from the base, right? So this is 2 meter from the apex, 3 meter, 2 plus 3 is 5. Okay, thank you, Nguyen. And next one, we have forces are F1, F2, X2. You want to find the location of the x. So here x is what? X is equal to f1 x1 plus f2 x2 divided by f1 plus f2. So the correct answer is this one. And also with this, can you work out the resultant? The resultant is area on this curve. So that area is 100 times 12 divided by 2, which is 600. FR is 100 times 12 divided by half, which is 600 Newton. And the line of action is 1/3 from the base. So 1/3 from the base is 4. And this is 6. So x bar, that is equal to 4. All right, so that is all we had for today. What we did, we introduced the concepts of machines and frames. So machines and frames are a combination of different members which are simply connected by pins. So we solved one example. Also, we learned about the pulley systems. So the pulley system, tension on both sides of the pulley are equal if the friction is neglected. And then we started the concept of distributed force. Distributed force in buildings are very common. And the way we handle them, we need to replace distributed load with a resultant force. It's not only magnitude of the resultant, also you have to find out the line of action or the location of them. And we went through example of those. All right, so that is for this. Make sure you come to the computer to the practical one that is in TD 30. And just bear with me. Let me finish the attendance. Okay, Nguyen is here. Chaisal left early. Daniel left early. And Barnaby is here. Flynn is here. And Darcy here. Portier here. All right. So that is, Daniel, is there a question? Do you want to explain something, Daniel? Just text or do you need clarification or anything, Daniel? Yeah, my mistake, my bad. Sorry about that. I already let you in. I take you in. Yeah, you're here. Maybe that was some email connection, but I take you as in. Thank you for that. Sorry, my mistake. All right, I see you all tomorrow in the computer lab. Take care. See you tomorrow. Thank you, Nguyen. See you.